Thank you to the organizers for giving me a chance to speak, and I want to thank a bunch of people before I get started, so I don't forget or run out of time. This is done at University of California, and I've just listed the names of people in the lab and also past lab members who've somehow worked on this project. This is done in the lab of Brian Schoikert. It's supported by the NIH, and I've listed the companies there at the bottom in alphabetical order, so there's no prejudice about who comes first. And so what we do is we try to use structure, protein structure, to find new molecules. So this is kind of a departure from almost everything you've heard up till now at this meeting. And the way we do that is called molecular docking. And so molecular docking looks like this sort of cartoon here. We start with the target of a protein. And there's a huge opportunity right now. There's something approaching 70,000 structures in the PDB and even much larger number of modelable structures based on homology modeling or comparative modeling. And we take a database of molecules depicted by this cartoon of pills on the right-hand side. And in the computer, we orient them and score them in the binding site, represented by these poses here in the middle. And then typically, the way we work is we then, because we can't afford to buy everything, we look at them critically and buy a small number of compounds, typically between 20 and 50, and we test them in the laboratory. That's our standard paradigm, and we're really, really happy if we find 2 or 3 completely novel molecules. Now you might think that's a pretty low bar of success, but each one of those represent, if they're chemically distinct, they represent opportunities for hit-to-lead optimization. So we're thrilled with that. And I'll just point out that this is complementary to a lot of what you've heard so far, ligand-based screening, where you start with a ligand or a set of ligands, and you look either via scaffold hopping or SAR, you try to find analogs. Docking has at least potential to find something really completely new that's not anchored with precedented molecules. And how do you know if docking is working or not? Well, so first of all, let me just tell you, in case it wasn't obvious already, that docking is really hard to do. It should be obvious because I told you that we were happy with just 3 compounds. And docking's hard for a lot of reasons. The internal energy of the protein, subtle changes in the protein can completely change things around. The energetics of the ligand just internally, very difficult to calculate. And then the interaction of the 2 of them, also very difficult. And one of the reasons why the interactions are difficult is because when you put a molecule into a binding site, you're displacing water molecules. And so there's an entropic cost of moving those water molecules out of the binding site. And there's so there's a large energy of interaction. There's a desolvation energy. These are 2 big numbers, and you're subtracting 2 big numbers to get a small number. So you can think about the errors involved. And actually, when I explain it this way, you can think, well, docking shouldn't even work at all. And yet, I'm going to show you a series of slides rather quickly, because this is all published, and the citations are listed below. But what you can see in each of these cartoons, and it's in your handouts, so you can look at this in detail later. But in each of these cases, you're looking at the result of a crystal structure that was done after a docking experiment. So docking makes a falsifiable prediction. It says, this molecule binds to this protein, and it does it like this. And we did the crystal structures, or Yu Chen and Brian did the crystal structures. And in many cases, not all, but in many cases, the crystallographic pose recapitulates or corroborates the docking prediction. So docking is working for the right reasons. And so this is an antibiotic target. So is this. We actually work on antibacterial targets in the lab. So there's the electron density, and there's the superposition of the 2 molecules. And so it's capturing the key, we believe it's capturing the key interactions between the protein and the ligand. And this is even the case where we predicted the function of a protein by docking a substrate into the binding site, and that was in Nature 3 years ago now. So you can read about that if you'd like. Again, it's all in the handouts. And so the reason for showing you all these slides so quickly is just to say that at least some of the time, docking is working correctly. But if you've ever worked on docking or known someone who works on docking, you'll also realize that docking does not work all the time, and it's got some very frustrating failures because the poses look perfectly good, they look reasonable, but the molecules don't bind. So docking has a real big false positive problem. Okay, that's the last of those slides. And so we want to investigate, why it is that docking works sometimes and doesn't work sometimes. And one of the problems with that is that docking historically has been a very artisanal affair. An expert sits in front of the screen and does a lot of tweaking of parameter files, and that really makes it difficult to investigate systematically the strengths and weaknesses of the method. And so in order to do that, we wanted to automate docking, and so we built an automated docking system. But first I wanted to just say that we found three problems that we found three obstacles. So this is like the metaphor of a chemical reaction. Three barriers to getting from a structure to the interpretation of a structure in the form of ligands that bind. And so I'm going to take you through those three barriers to automation of docking. So the first one, really simple. It was just the availability of a suitable database. When we started out, the ACD was the standard database. I know we've heard numerous talks that have mentioned putting together databases. You guys are terrific. It makes it look really easy. But believe it or not, there was no such thing as a public database, so we built one. And this was about six years ago now. Actually, I mean, we've been doing it, as was everybody, for a long time, but we just made it public about 5 and a half years ago. And so it's called ZINC, and it's on the web. It's completely free. It contains currently about 32 million molecules you can buy. It's updated continuously. We create subsets that people tell us that they like, that are well regarded in the community. Drug-like criteria, rule of 5, rule of 3.5, rule of 2.5. So if you're not familiar with those terms, don't worry. It's just sort of increasingly small molecules. And this was published. We make it available in various formats. The idea is to completely eliminate the database as a barrier to entry to structure-based docking. Really rapid turnover. We load about 10,000 new molecules a day. There's just an unbelievable amount of new synthesis going on, particularly coming out of Kiev. And so the reason I'm here talking to you today is because although we weren't really interested in searching zinc molecule by molecule. We were mostly interested in docking entire libraries and seeing what happened. But a lot of people wanted to use zinc for searching molecules. And the original search tool we put together was terrible. We're going to do a live demo. Okay, so this is what the new search interface for zinc looks like. And it's got a little, okay, this is a real live window. John. Yes, okay. So this is what the search interface for zinc looks like. So you just go to our website, and there's a little powered by ChemAxon logo down in the bottom there, okay? And so there's the interface, and this is a molecule I was just reading about. It was in the news. It's interesting, apparently this is a drug both for itchiness and for insomnia, which I thought was an interesting combination, depending on how you formulate it. Yeah. So the nice thing about our interface is that you can just edit the smiles, and then you can update the editor. So if you can just add more smiles over here, and you can update the editor. So depending on or you can go over here, and you can add a new moiety, and it updates the smiles over here. So you can sort of go back and forth, so depending on which one you're more comfortable with. Okay, and then you can search for similarity or substructure. There's lots of additional criteria to search for. You can either bring those to the front. They're all down the bottom, or you can use this navigation panel. I'm spending more time on this than I intended to. So I'm just going to do the search now. So you just say run query when you're ready. And I swore I would never do this again. running a live demo in the middle of the search, but it worked. Thank you. That was 5 seconds, 32 million molecules, or it terminates after it finds 10,000. It actually found, it looks like 6, so that's fine. Okay, and so these ones were actually inside PubChem, because I didn't specify they had to be purchasable, but some of these ones are purchasable, and they even have e-molecules numbers, and you can just click on it, and it takes you to e-molecules if you want to use them for the purchasing. All right, so let me just explain to you a little bit about how we integrated ChemAxon in there behind. The previous search was terrible. I won't tell you how that worked. So the query that you saw goes to our web server, which is written in Apache, Perl and Python applets, or whatever they're called, scripts, CGI script. And then, so we wanted to do the minimum amount of disruption to our existing system, because we don't have a lot of time to do this. It's a university, so we're doing publishable work, and I can't get anyone to publish this. So, so basically what we did was we just run curl. We set up a Tomcat server, and we use curl to send a query over to the Tomcat server, which then in turn talks to ChemAxon. It's the JChem. It's not the cartridge, okay? It's the other one. And ChemAxon nominally has MySQL that it pulls the data out of. ChemAxon returns in like 0.5 of a second. So most of that 5 seconds you saw was my slowness, not ChemAxon's. Back to Tomcat, back to my Python script. And then we go, because we've still got all of our old properties and things inside ZINC, so we go to the old ZINC database, come back, and then we deliver the results. And that whole round trip is typically around 5 seconds, about 0.5 of which is spent inside ChemAxon. So the benefits for us of using ChemAxon were that it was just unbelievably fast. I still don't understand it. And of course, I'll never will, because it's all locked up, isn't it? It was a simple interface. It was trivial using curl to interface in a kind of a way where we didn't have to make a big commitment. It was just very, very modular. And it seems to support a large number of concurrent queries and very graceful degradation. This is publicly exposed. We have almost effectively no limits. People hit our server all the time, and we never see significant slowdowns. Okay, so thank you, ChemAxon, for making my life so easy. Let me tell the rest of my story. I want to tell you about 2 more barriers to why automating docking has been difficult in the past. So the first one was the database, and so that's sort of pretty well sorted out now. The second thing that makes docking hard to automate is actually running the docking. Okay. All these things like preparing the hotspots and parameterizing it and all this sort of thing. And so we built an automatic docking pipeline which really tried to just capture everything that we were ourselves doing as experts in the laboratory. And this is very symbolic level, but what you'll notice is that it starts with as little as a PDB code, and that it has quite a few failure modes, places where it just gives up. And so our approach has not been so much to try to write a universal docking program that will work every single time, but rather to write something that we could understand, that would sort of fail cleanly, and then we could then sort of figure out where the weaknesses of our protocol were. And so just like experts in the lab, when we do docking, we would often do an initial docking, and we'd look at the results, we'd say, I wonder how sensitive it is to the degree of sampling we're doing, or I wonder how these results would depend if we change the scoring weighting scheme a little bit. And so we do the same thing in the automatic procedure. We try docking 4 different ways, so there's 4 shots on goal, and we just take the best one. And you're going to say to me, well, how do you know which one is the best one? And so before I tell you how you know which one is the best one, let me just say that once we had built an automatic docking pipeline, we were able to create a web service. This is a web page that supports docking, so you can come to our web page, and without registering, we don't know who you are, except for your IP address. You can start docking you can start with a structure, so a PDB file that you've manipulated, or you can start with a PDB code, so just give us the one ABC kind of code. Or if you can't think of which protein you want to dock to and you just want to see what the program does, you can choose the I'm feeling lucky option. And so this is what it looks like. It's kind of old and clunky looking, but it's what I can write. And so you just type in the PDB code and you click on dock like that, and then it goes off and does stuff. And so that was the automation procedure of docking. But the problem with, if you've ever worked on docking or know someone who's worked on docking, you also know that docking can produce a whole lot of garbage in a hurry. And that just looking at the results, it's sometimes difficult to tell which runs are good and which runs are bad. And the people spent a lot of time thinking about this, and so we realized that we had to too. And so the third barrier to docking success is the assessment part. So, is docking working or not? Okay. So this is what the results look like. Typically 20 minutes, but it depends a lot on the nature of the binding site and various other things. But I really wanted to show you here. Basically, we start here, preparer, scrutinizer. We do target preparation. We do calibration. So we dock some molecules to, in a sense, calibrate the docking. Remember I said we tried it 4 different ways? So we try 4 different ways, and we try to infer what the best parameterization is and whether docking is working or not. But the purpose of this slide is just to show you what the results look like. You end up with some information like it's the first molecule in the list, and it's got a serial number, it's got a score, it's got a picture. You can buy it from various sources. It's got some molecular properties. And if you click on these buttons at the top, either Chimera or PyMOL, then it takes you into a session that looks like this, where you can navigate and look through the top 500 scoring molecules and just look at the interactions and second guess the program and say and think to yourself, do I like these molecules or not? So that's one form of assessment. Of course, it's just your opinion, and even if you have a team of medicinal chemists famously disagree with each other about what constitute good molecules and good poses. So you really do ultimately need to test them. That's the only way, and I showed you that at the beginning of the talk. You can do crystallography, but there are ways to test also retrospectively. It's really the only way if you're going to benchmark a program systematically. You can't always be doing prospective experiments. And so the first way we came up with for self-assessment, so this is something that can be automated so we can do it on a proteomic scale, is we limited ourselves only to those proteins where there's a ligand in the binding site that our program could identify by itself. And then we take that molecule out and we reduce it back to its topology, SMILES, and then we build it back up to its 3-dimensional structure or structures so that we have no crystallographic bias in the ligand, so that it's fair. And then we ask 2 things. One is, can we recapitulate the pose of that ligand in the binding site? And second, because that's the minimum, if you can't recapitulate the pose, it's not necessarily the end of the world, but you really wonder if your docking program can't do that, if it can work at all. And the second one is, does the molecule score well, and compared to what? Well, compared to other molecules that you might expect would also bind. And those molecules have similar physical properties like molecular weight and log P, and yet they're chemically different, and so reasonably you'd expect them not to bind. On the other hand, if all you need to do is be big, like HIV protease, you might do well no matter what you look like if you're a molecule. Okay, and so then we have, at the end of this sort of single molecule-based self-assessment, because all we've started with here is a PDB structure, we have this kind of traffic light system for saying, well, if you get the pose right and you get the rank of a ligand right compared to these decoys, then that looks pretty good, and you should trust the docking, or at least invest more effort into it. And if something went wrong, like you can't recapitulate the pose or the rank is poor, then either you should not trust it or something like that. And so this was how we published it last year. One of the things that came out of that work was just that we noticed that here, this axis is the pose fidelity, so how well we recapitulate the pose in the binding site, and here's the rank compared to our decoys. And what you notice is there's no relationship between the two, basically, that if you get a good pose, you might get a terrific rank, you might get a lousy rank. So RMSD is no prediction of the fact that it's going to score at the top of the list, which means, well, so we applied this method to a large benchmark, and here success, our definition of success is both pose and rank of a single ligand. And you look at these numbers and you think these look a lot smaller than most people in our field claim, but they're still pretty interesting when you think that most people don't report these kinds of numbers. Most people report pose recapitulation. And so what you can sort of infer from this is that maybe 20% of the time you can get good docking results from a fully automated black box, hands behind my back docking approach that you could apply to the entire proteome. And you know which ones they are. Okay, so because you can run this automated analysis. But of course, there is a problem with what I just told you, and we noticed this ourselves, and that was that there can be funny artifactual things about the particular ligand in the particular structure. So the molecule might be very flexible, for example, and so there's just a sampling problem to recapitulate the pose, but the docking actually looks pretty good when you look at the other ligands. And so we wanted to move to a method that was not so dependent upon the single ligand metric, on the failure of a single ligand. And so we looked at the intersection of two databases, the PDB, the database of all structures of proteins, and the database called ChemAxon, which is the medicinal chemistry database out of EMBL in England. And so we looked at still just the proteins where there's an identifiable ligand, good quality structure. And on the right-hand side here, we looked at all the cases where there were sufficient number of good affinity ligands. Our cutoff was 10 micromolar. You could do it at 1 micromolar or 100 nanomolar. You'd get slightly different answers. I think you'd get largely the same results. And we get more coverage this way. And so, and we used the UniProt code to map these together. So we found 733 ligand sets that intersected with 7,400 PDB structures. And so with each of these cases now, we can do an assessment because we can say, can you use docking automatically to recapitulate what we already know? These ligands bind. Can you rediscover them in a database? And so when we do this, our automated procedure, so we're able to, our completely black box system is able to find the ligand and get started in about a little less than 5,000 of the cases. And it finishes in a little more than 4,000 of the cases. And in around 2,500 cases, and these numbers are still evolving, we get what looked to us like pretty interesting enrichment results. That is to say, docking, black box docking, can rediscover literature ligands and put them near the top of the list. And so we were able to assess this quantitatively, and so I'm going to introduce a kind of graph that we use in our field. So this is called a receiver operator characteristic curve, ROC curve, and so the vertical axis in this graph here is the number of ligands that have been found, and on the horizontal axis, it's the number of decoys. The decoys is the rest of the database. And so this curve here, this curve, it's a semi-log scale, so this is random performance. So if you just randomize the molecules in the database, you'd still expect to find some of the ligands at some point, yeah? And to the extent that this curve goes above the random, it means that your docking program is enriching known ligands towards the top of the list. And so we integrate the area under the curve, and this is our metric of success. How much better are you doing than random? 2 minutes? 3? 2. Okay, so, and so when you rank them here, so here's, for the 114, I'm going to tell you about 114 systems, and for 114 systems, the best ones get scores of about 45 area under the curve. Okay, so these numbers are meaningless to you. It's good, okay? And down here, there's a small number that actually do worse than random. So 0 is random performance in the way we've done this. And so we're showing you the results for 114, and here's the numbers. Go back. So by the multi-ligand metric, more than half the time, we are able to get compelling-looking docking results in our estimation. And so this is much better than the single ligand metric that I showed you earlier. So we're quite optimistic about this. It gives us lots of avenues for investigation. For instance, we can say, why is the automated script not working for these systems, and why does it work so well for these? So it's given us a set of tools to systematically evaluate docking performance in a way that really hasn't been done up until now. And so in order to leave a couple of minutes for questions, I'm going to stop there and thank you for your attention.
Nice talk, John. So did you look at the relationship between the topological similarity of your actives to the cognate ligand in the crystal structure? Because it would be interesting. My suspicion is that the cases that worked best were probably the things where you had either the chemical ligands were either the crystal structure or something very close.
Mm-hmm. Yeah, so if I told you about some of these ones up here, urokinase, factor 10A, there's some sort of maybe very common motifs there. These ones down here, on the other hand, tended to be kinases, and you're thinking, oh, that's strange. But in kinases, with our docking program, it's not so much necessarily the topology, but you have to do a particular treatment to these backbone residues, or else you don't get good results. So you have to basically create some bias. And our automated program doesn't include that. So my interpretation of this is more, it shows which systems we've worried more about. Yeah, but thank you for the suggestion.